Good morning, everyone. My name is Mr. Lee, a senior engineer in petroleum engineer. Today, I will lead us to have a learning about the petroleum engineering. Petroleum engineering is very important for the oil and gas industry. We should know how the whole process of the petroleum engineering. So today, the first I will make the introduction about the petroleum engineering. The contents will have what is petroleum engineering and what does petroleum mean, and generation of petroleum and chemical composition of petroleum and petroleum products and fractional distillation and the history of the first oil wells. So what is the petroleum engineering? I think for our workers and employees will have this question. The petroleum engineering is an engineering discipline concerned with the activities related to the production of hydrocarbons, which can be either crude oil or natural gas, and also considered as upstream sector of the oil and gas industry, which are the activity of finding and producing oil and gas. So we can say the petroleum engineering is one of the very important activities to find and produce the oil and gas. So what is the petroleum engineer? A petroleum engineer is a position is involved in nearly all stages of the oil and gas field evaluation, development, and production. The goal of a petroleum engineer is to maximize hydrocarbons recovery at a minimum cost while maintaining a strong emphasis on reducing all associated environmental problems. We can say this is the three high important things. The first is the maximum oil and gas recovery. The second is minimum cost. And third one is to reduce environmental problems. So the petroleum engineering are divided to several groups. The first group is petroleum geologists, who find hydrocarbons by analyzing subsurface structures with geological and geophysical methods to find the oil and gas. And the reservoir engineering. The reservoir engineer who works to optimize production of oil and gas through proper wells placement, production levels, and enhance oil recovery techniques. And the drilling engineer who manages the technical aspect to drilling, exploration, and production and injection wells. It also includes the mud engineer who manages the quality of the drilling fluid. And third one is the production engineer. Also includes the subsurface engineer who manages the interface between the reservoir and the well, including preparations, sand control, downhole flow control, and downhole monitoring equipment, and evaluate artificial lift methods, and also select surface equipment that separates the produced fluid, the oil, gas, and water. So these four positions are very important for the petroleum engineer: geologic and reservoir engineer, the drilling engineer, production engineer. All this is upstream sector for the oil and gas finding, evaluation, drilling, production, and all of this. So where does petroleum engineer work? We can divide for the employer, some people from the government, some people in the oil company, some people in surface company, and support is the supporting company, and also the academic for the research and others. The location of these different peoples, some work in the office, some work in on-land oil rig, some in the offshore oil rig, and land production platform. We can say the field and offshore production platform. This is the location. So what does petroleum mean? The petroleum literally means rock oil. It means rock oil, the oil in the rock. The word comes from the Greek word petro. It means rock, and the Latin word oleum. It means oil. So it can say the oil rock. And the word petro is a shortened version of the petroleum. Petroleum products are all the substances made from the petroleum. We can say the first is crude oil. The crude oil we can understand is called crude oil. Crude oil is made of a mixture of different chemicals called hydrocarbons. These were produced when tiny plants and animals decayed under layers of sand and mud. And crude oil doesn't always look the same. It depends where it comes from. And sometimes it's almost colorless, or it can be thick and black, but crude oil usually looks like thin brown tricycle. When it comes out of the oil well, especially an undersea well, the crude oil is often mixed with gas, water, and sand. In the wiki-packy, the crude oil, we can say the petroleum or crude oil is a naturally occurring toxic flexible liquid and consists of a complex mixture of hydrocarbons of various molecules with and other organic compounds that was found in geologic formation beneath the Earth's surface. And the petroleum is recovered mostly through the oil drilling. It's refined and separated most easily by boiling point into a large number of consumer products, from gasoline and clothing to asphalt and chemical reagents used to make the plastic and pharmaceuticals, which is our human all used in the life. So what made oil? It means what the oil made from. The oil in the tin animals and plants that live in the sea are called plankton long years ago. The plankton that lived in hundreds of millions of years ago made our crude oil. And when they died, they sank to the bottom and slowly got buried by sand and mud. Over millions of years, the dead animals and plants got buried deeper and deeper. And then, by the heat and pressure, they gradually turned the mud into rock, and the dead animals and plants into oil and gas. So, what's the meaning of the hydrocarbons? The hydrocarbons, the crude oil is a mixture of hydrocarbons. They are often the chains of carbon atoms with hydrogens attached. The longer chains have higher boiling points, so they can be separated by distillation. The simplest groups are the alkylates and alkylates. They all end the "any" in "any" respectively. The first bit of their name depends on the numbers of the carbon atoms. So the right photos talk about the alkylates and alkylates, the different chains of the hydrocarbons. So what's the generation of the petroleum? How's the petroleum generation? The petroleum generation takes place in source rock. Here marks take place in source rock. The source rock, which may be defined as organic rich, fine-grained sediments deposited under no energy reducing condition. And most commonly, petroleum source rock contain a minimum 0.3 to 0.5 by weight of the organic matter. And also, preservation of the organic matter is the key to the development of the potential source rock. Also environment, very important. The environment of source rock deposition is therefore characterized by a relative deep, unagitated, no energy body of water with an oxygen-starved bottom but abundant life at the surface. And also the non-hydrocarbon organic matters, we can see the kerosene is the major source of oil and gas deposit. And the generation of hydrocarbons from the source material depends primarily on the temperature to which the organic material is subjected. Hydrocarbon generation appears to be lineable at a temperature less than 150 Fahrenheit in the subsurface and reaches a maximum with a range of 225 to 350 Fahrenheit. The hydrocarbon window, we can see the hydrocarbon window. Increased temperature converts the heavy hydrocarbons into lighter ones and ultimately to gas. However, at the temperature above 500 Fahrenheit, the organic materials is carbonized and destroyed as the source materials. Consequently, if source beds come too deeply buried, no hydrocarbons will be produced. And then we will talk about how the kerosene conversion to oil and gas. The anaerobic bacteria convert to lipids, fat, oil, and wax, and then into a waxy substance called kerosene. Remark here, kerosene is from the anaerobic bacteria convert to lipids and then to the kerosene. And during the burials of sediments, the increase in temperature results in a progressive change into the composition of the kerosene. 3 successive stages are distinguished and refers as diagenesis, catagenesis, and metagenesis. Very important 3 stages. The main trend is a continuous increase in carbon contents of kerosene. So we will talk about the 3 phases. The first one, diagenesis. Diagenesis of kerosene is characterized by an important decrease of oxygen and a corresponding increase of carbon content with increased depth. CO2, HO2, and some heavy NSO compounds are released. And then the source rock are considered as immature at this stage. The next stage is cartogenesis. Cartogenesis is a significant decrease in hydrogen content and in the H2C radio takes place due to the generation and release of hydrocarbons. This is the main zone of oil generation and the beginning of the cracking phase, which produces wet gas with a rapidly increasing proportion of the methane gas. And third stage is the metagenesis. Begins at a temperature exceeding 175 degrees. During this stage, a rearrangement of an aromatic sheath occurs, and the stacks of the aromatic layers previously distributed at random in kerogen now gather to form larger cluster. At this stage, only dry gas is generated. The next table shows the color of the kerogen change as it matures. The first column is color and maturity level and diluted H2C, HC. The yellow is immature and biogenic methylene. The orange is mature, the oil. The brown is mature, the wet gas. And black is the metamorphosis, is dry gas. In this photo, it shows you about the general scheme of the kerogen evaluation presented on the Van Crovanes diagram. This is also very important. Next one, we talk about the chemical composition of the petroleum. What is the composition? The substances present in petroleum fall into four major groups. The first one is paraffins. The second is naphthalene. The third one is aromatics, and also the non-hydrocarbon. The relative proportions of these compounds determine the physical property, the density, the viscosity, the pour points and others of the petroleum. So the first we talk about the paraffins. This photo talking about the different structures, same formula, and name of the paraffins. Yeah, we can see these four. Yeah, for the carbon to 1 to 4, and also to the 18. 1 to 4. Yeah, to the 4 we can see it's a gas, and above number 4 and 2 other is the liquid, and over 18 is solid. So there are also known as the aliphatic hydrocarbons. They include the alkalis, which are saturated and have the generating formulate CnH2n plus 2. They can say the methane, acids, and the alkalis, which are undersaturated and have the generating formula CnH2n or CnH2n depth n, and the carbon atoms are joined together to form chains. The second is left-stylus. Left-stylus is also, they are referred to also as cycloperfumes and are characterized by their carbon atoms joined in such a way as to form a ring. Like this, form a ring. The heavier MW fraction of the petroleum often contains quite complex left-stylus molecules with two or more rings joined together. The next one we talk about the aromatics. The aromatics is the basic building blocking of these hydrocarbons is the benzylic ring. The aromatic structure occurs especially in the high molecular weight fraction of petroleum. And then we talk about the non-hydrocarbons. The non-hydrocarbons is only like NH. Compounds in this group contains nitrogen, sulfurs, and oxygen. And free nitrogen gas may be generated during the formation of petroleum. And sulfur organic compounds are often full smells. The best known is H2S. And also the oxygen compounds includes the alcohol, ethers, and organic acid. The other, just now we talking about the four compounds of the chemical compounds of the petroleum. And then we talk about one very important the process, the fraction distillation. Fractional distillation splits the crude oil into simpler mixture called fraction. The different fractions are taking out the steer at different levels. This happens in a distillation tower, which we shorten to steer. The crude oil first is heated in a furnace to about 350 degrees and is pumped into the bottom of the distillation tower. Most of the hydrocarbons are gases, and though the very thick ones are still a liquid even at these temperatures. This is the tower. We can from the hot crude and to the down, and hot vapors rising to the top of the tower were cooling liquid and falling down to the crude oil and then CO2. So the tower is like a giant heat exchanger. It removes heat from the gases as they rise up it. The temperature falls to 20 degrees by the time of the vapors reach to the top. The vapors condensate as they rise up the tower. The heavier ones with higher boiling point condensate first. The thinner running ones get further up the tower before the condensate, and the gas pass out of the top. So where do product come out of the steer? Yeah, we can see this is the temperature. Temperature very important from the top to from the bottom to the top. We can see the different degrees. You have different the result. Here we can see the over 409 degrees the fuel oil, and then above is the lubrication, and then is the heavy oil, gas oil, and then the light gas oil, and then the kerosene and the lufters, and the top of the tower is gas. So a distillation tower splits crude oil into separate fractions. Each fraction is a mix of hydrocarbons. Each fraction has its own range of boiling point and comes off at a different level in the tower. In reality, a single tower could not cover the full range of the temperature needed to split up the heavier fractions. So this table, just like we also talking about, this table shows the length and the use of the fractions that comes from the distillation process. It also shows the range of the hydrocarbons in each fractions. The fractions, we can say the fractions and the carbons 1, 2, 4, and the boiling points and uses. Yeah, we can say the gases is the carbon 1 to carbon 2, 4, and the boiling point is very less than 40 degrees. We use it for the fuel in refines, bottled and sold as LPG, the gas. And then the left side is 5 to 10, and the boiling point is 25 to 115. It's blended into petrols, the feedstocks for making chemical. And then it's the kerosene, yes, is the carbon 10 to 16. The boiling point 150 to 260 is the aviation fuel. And then the light gas oil is the 14 to 15. The boiling point is 235 to 360 is the diesel fuel production. And then is heavy gas oil is the carbon 20 to 70. The boiling point 330 to 380 is the feedstock for the catalytic cracker. And the lubrication is the hydrocarbon over 60, and the boiling point is 340 to 575 is the greases for lubrication, and the fuel additive and feedstock for catalytic cracker. And the fuel oil is also over 70 about the carbons, and the boiling point is over 490. It's used for fuel oil. And last one is the bitumen, is the over 80 carbon and over 580 for the boiling point, is for the road and roof surface. So this is the table. The names and the use of the fractions come from the distillation process. So in the chapter 1, the last one we were talking about the history of the first oil well. It makes a very big influence of the world petroleum industry. The modern oil industry dates back about 150 years. The world's first oil well was drilled in Titusville, Pennsylvania in 1859. It strikes oil at 21 meters below ground and produced 3,000 liters of oil one day, very high productions, and also knowing as the dark well after the colonel Edwin Drake, the man responsible for the well. It began an international search for petroleum, and in many ways eventually changed the way we live. Okay, so this is the first chapter. We can have the summary. This chapter we talk about what is the petroleum, what is the petroleum engineer, what is the petroleum compositions, and also from the generation of the petroleum, and also the composition of the petroleum, and how the distinguish the process and the history of the first oil. This is just an introduction to let you to know what's the base introduction of the petroleum. So from next chapter we were talking about the whole technical process. Hello everyone. For this chapter, we entering the petroleum engineer. The very important one. The first one is in this chapter we'll talk about the geologic and exploration in the first step of the petroleum. So in this course we were talking about the rock types. Just now we talking about in the last chapter we talk about very important is the source, the rock oil. We call the rock oil. So the rock type, which rock contains of the oil and gas, is very important. The second is parameters controlling petroleum occurrences. How to control the parameters. We can get how to of this information, and also talking about migrations of the petroleum. It means the rock in the known history, how to the migration to the petroleum, and also the entrapment of the petroleum, and also the oil exploration method. In this chapter, we will talk about the source of the oil and how to identification and how to different the rocks is very important. So first we will talk about the rock types. The first is igneous rock. Igneous rock are crystalline solid which form directly from the cooling of magma. This is an axiomatic process. It loses heat and involves a phase change from the liquid to solid state. And the igneous rock are given names based upon two things, very important two things: composition, is what they are made of, and texture, how big the crystals are. The texture relates to how large the individual mineral grains are in the final solid rock. In most cases, the resulting grain size depends on how quick the magma cooling. In general, the slower the cooling, the larger the crystal in the final rock. The other factor is composition. It means the elements in the magma directly affect which mineral are formed when the magma cools. Here has the examples of the igneous rock. One is the granite and another one is basalt. So the second is talking about the sedimentary rock. The sedimentary rock are called secondary because they are often the result of the accumulation of small pieces broken off the pre-existing rock. This accumulation get compact and cemented together. There are three main types of the sedimentary rocks: elastic, chemical, and organic sedimentary rock. So the classic cemented rock are accumulate of the clusters, little piece of broken up rock which have compact and cemented. Example of the classic sedimentary rock are sandstone, shale, siltstone, and conglomerate. So here have four photos talking about the sedimentary rock. The first one is sandstone, the shales, and also the siltstone and conglomerate and different formations. And second is the chemical sedimentary rock. Many of these form when standing water evaporates, leaving dissolved minerals behind. Thick deposits of the salt and gypsum can form due to repeat fluid and evaporation over long period of time. The example of chemical sedimentary rock are gypsum and Dolomites. These photos show about the different the gypsum, the Dolomites. Okay, the third type of the sedimentary rock is the organic sedimentary rock. It means any accumulation of sedimentary debris caused by organic process. Many animals use the calcium for shells, bones, and teeth. This bit of the calcium can pipe up on the sea floor and accumulate into a sea elastic layer to form an organic sedimentary rock. Examples of organic sedimentary rock are coal and coquina. These photos, 4 photos there. This is the chemical sedimentary rock. It's gypsum and Dolomite. This two is about the organic sedimentary rock, the coal and coquina. So the third type of the rock is metamorphic rock. The metamorphic gets their name from metal and morphic. So any rock can become a metamorphic rock. All that is required for the rock to be moved into an environment in which the minerals which make up the rock become unstable and out of equilibrium with the new environmental conditions. In most cases, this involves borate, which leads to a rise in temperatures and pressure. The metamorphic change into metals always move in direction designed to restore equilibrium. The common metamorphic rock includes slates, schist, jellies, and marble. Yeah, this is 4 photos about the example: the slate, the schist, the marble, and jellies. So just now we talk about different kinds of sedimentary rock. So here we talk about the parameters controlling petroleum occurrences, the very important parameters. The first is source rock. The source rock is fine-grained sedimentary that, in its natural setting, has generated and released enough hydrocarbons to form a conventional accumulation of oil and gas. Source rock are clay or carbonate organic rich marls deposited under no energy reducing condition. The most important factor in the generation of petroleum in source rock is temperature. The action of heat on the insoluble organic matters we call corrosion contents in source rocks leads to the formation of the oil and gas. So the source rock is very important. The second is reservoir rock. Reservoir rock. The petroleum reservoir is a porous and permeable rock in combination with a natural source bed. Sandstone and carbonate rocks form the overwhelming majority of reservoirs worldwide. Under special circumstances, engineering and metamorphic rock can also act as petroleum reservoir. The third one is talking about the traps. A trap is an arrangement of rock layers that contains an accumulation of hydrocarbons, yet prevents them from rising to surface. The trap consists of an impermeable layer of the rock above the porous permeable layer contains of the hydrocarbons. It can be structured traps or stratigraphic traps or combined of these factors. Structural traps occur when the reservoir formation deforms. Stratigraphic traps are those where porosity or permeable has changed with the formation. The trap is very important to avoid the oil and gas to out evacuation. So the migration of the petroleum also important. Oil and gas move out of the surface, the source beds, and accumulate in the reservoir rocks. The transfer from source rock to reservoir rock is called primary migration. The primary migration is transfer from source rock to reservoir rock. The movement of petroleum within porous and permeable reservoir beds is known as secondary migration. The primary cause of the movement of fluid is compact. The more permeable silt and sand bodies with compacting moves are the main channels of the fluid migration. So this photo is the direction of the fluid migration into the anticline. We can say in shale sand reservoir. To like this. The second photo is a migration from the interbedded shale sand sequence. It's like this. And also this is the migration into the penasical reef. It's like this. And also the migration into stratigraphic traps is like this. It's like this, different. So next we talk about the entrapment of petroleum. Oil gas water slowly migrate through permeable rocks, driven by natural force of gravity. We can see the buoyancy and pressure gradients. Two important. The first is the gravity and pressure. When they meet an impermeable barriers, they can go no further. So oil and gas accumulates. This barrier is generally referred to as a trap. Varying density makes the gas phase rising, while the water sets to the lowest point and oil remains in the middle, the gas in the top. The traps may be classified according to the manner in which they are formed and categorized as structural trap, stratigraphic trap, and combination trap. The three kinds of the trap. The structural trap, it's like the photo like this. This is the anti-collision oil trap. It's like this. The oil is here. And also the structural oil trap caused by faulting. You can see different faulting layers. Oil can be here. So by far, the greatest number of the field discovery worldwide and largest proportion of the total premium reservoir are associated with the structural traps. Structural traps is the most weighted. The structural trap results from a local deformation such as the folding and the faulting of the rock layer. Faulting can also produce trap by choose trap position or reserve against an impervious structure. So the draping and or compacting over a bird here combined will also produce the trap on the smaller scale. This is the sedimental drops. The drops can also cause the traps smaller scales. The second is about stratigraphic traps. The most basins contain phase changes and conformities which result in truncated beds and birds, erosional or constructive surface such as reef, hills, barriers, sandbars, channels, and other related geologic phenomena which form the basic requirements for the creation of stratigraphic traps. Stratigraphic traps is a generic term for the traps that are chiefly the result of the natural variation in the lithology of the reservoir rock or a break in its community. A permeable reservoir rock changed to a less permeable or to an impermeable rock. Two common types of the stratigraphic traps are the pinch-out type or truncated type. So these two photos shows the two different types of the stratigraphic trap. The first one is the pinch-out type. We can see this is like this. Yeah, the reservoir rock, reservoir rock, and water is here, and here is oil. This is also the trap, and gas is here, cannot to move out. It's like this, and also the truncated type is like this. The roof rock is here, and oil is here. This is the reservoir rock. It's like this. So the third one is combination trap. Combination trap is the geometry of this type of the trap is the result of the combination of the tectonic process and change in lithology. It's like this. It's like this. We can see it's like this too, like this. A common trap that would be an example of a combined trap is a short dome. This is very difficult to drill like this formation. So just now we talking about the different types of the trap. So continue. We talk about the oil exploration methods. It means how to find the oil. Where is the oil? In the earlier days of the petroleum, most oil finds were the result of the digging or drilling near known oil and gas seeps of accident find were drilling for water. Yeah, in the earlier days we find oil like this. A good definition of a seep is means the surface expression of a migration pathway along which petroleum is currently flowing, driven by buoyancy from a surface origin. At the most basic level, this demonstrates that the basin contains a generation source rock and hence a variable petroleum system. It means we are able petroleum system. So for the surface geology, we use remote sensing method. The selection of effective exploration targets is an important step to achieve success in oil exploration. The remote sensing refers to using infrared or other means to map an area, map a big area. This method is used to study the basic of petroleum geologic conditions. And also, the remote sensing imaging has characteristics of the reality and provide accurate visual data for directly determining geometric shapes of the sedimentary basins. And the remote sensing techniques are more effective and useful for understanding and studying those basins in the out-of-the-way mountains and remote deserts. And the remote sensing equipment can be carried by airplane and by satellites. And the company using remote sensing data, however, still leaves traditional exploration information to pinpoint the location of the commercial deposits. So just now we're talking about the surface geologic. In earlier is from the to sea, and then use the remote sensory data. We can use the two description, the big map on the area to see. So this moment we're talking about geophysical exploration. The geophysical exploration, the first is magnetic methods. The sedimentary rock generally have a very small magnetic susceptibility compared with inglacious or metamorphic rocks, which tends to be a much higher magnetic or common magnetic mineral content. So this is very important. The sedimentary rocks generally have a small magnetic compared with others. So by conducting a magnetic survey over a given area, a prospector can determine where oil-bearing sedimentary rock is more likely to be found. We use this method to find the oil-bearing sedimentary rock. And the magnetometer is used to measuring the magnitude of the Earth's total magnetic field over a large area. So it's one of the very important tools. A magnetometer can be towed behind a ship or an airplane to cover large areas. It transmits data to a device on board which records the information onto paper or magnetic tape. A development of the airborne magnetic is the micromagnetic technique for oil exploration. An airplane towers are micromagnetometers from a low altitude, normally about 3 feet above the ground. It detects micromagnetic anomalies and or deviation from the norm. So use this very important. The geologic use this data to be predict the characteristic of the overlying sediments. So the second one is the creative methodology. Because the Earth's gravitational attraction varies slightly from one place to another on the Earth's surface. Some of these variations occurs because of the Earth is not a perfect sphere, and some is related to difference in elevation on the Earth's surface. For example, in north-central Kansas, this is an anomaly known as the middle continent gravity high, where the Earth's gravity is about 0.005% greater than normal. So the difference, we can find different. In gravity perspective, geophysics measures variations in the force of the gravity from rocks up to a few miles beneath of the Earth's surface. So the different types of the rock have different density, and the denser rock have the greater gravitational attraction. If the higher density rock formation are arched upward in a structure height, such as an anticline, the Earth's gravitation field will be greater over the axis of the structure than along its flanks. And also a short dome, on the other hand, which generates less dense than the rocks into which is intruded, can be detected from the no value of gravity recording compared with the measures on either side. So we use this for the gravity. So the third one is seismic method. The seismic reflection, a powerful technique for underground exploration, has been used for over 60 years. It will give more precise details on the formation beneath the surface. The seismic wave, very important, seismic wave are inertial sound waves that travel underground at the velocities of 2 to 4 miles per second. It means 3 to 6 kilometers per second. Depends upon the type of rock through which they pass. So the reflections are recorded by detecting instruments responsive to the ground motion we call geophones. They are aligned among the ground at distance from the shoot point, which are generally small compared with the depth of the reflector. So, according to the variations in the reflection time from place to place on the surface, usually indicated structural features in the strata below. So, from the geophones, the wave will be sent through cables to a recorder. The recorder, a seismograph, amplifies and records the wave characteristic to produce a seismograph. And then the seismograph generates a seismic section, which is a two-dimensional slit from the surface to the Earth downward. And then the information from a seismic survey indicates the type of the rock, their relative depth, and where a trap is present. So this is the whole process and method of seismic. So this photo is showing the onshore seismic operations. So we can see from here, this is the seismic track from here, and cable here, and then have the wave. This wave have different to here zigzag and to get the information for the geophone and then transfer to the truck and then transfer to the computer process of the system data. And use this, we can define different kind of the rock and these photos, the rock formations, for the different types to get the photo and image of these errors. So it's very useful to find the oil and gas, the source rock. So the next one we talk about the subsurface geophysics exploration. We use the well correlation. It means consists of the establishing correlation by merging structures, rock hardness, and or surface, and the electric and radioactivity data to determine the origin, composition, and the distribution of rock stratas. To the electric logs, radioactivity logs, and acoustic logs help geologists predict where oil-bearing structures occur. The sample logs combined from well cutting and cores are used to identify the key baths and lithologic sequence. So the core sample are taken from the top to the bottom of the well and show rock in sequential orders as it appears in the ground. The core sample also provides information on porosity, permeability, and saturation of the rock in the well. And cuttings are continuous record like core sample, but provide a means for identifying sections with larger thick layers through the fossil and mineral deposits. So it's also very important. So the second chapter we talking about the geologic of the very important is we find the sock rock. We use different methodology like the megalithic, graphite, and seismic. These three types of different the method, and also we can use the well correlation with the log, the different log, and also with the core samples and the cuttings to make the well correlation to find the layer of the field and measuring a layer of the formation provides very important parameter to us to find the sock oil. So then we go to the next. It's very important for our the petroleum. Now we continue to the next chapter to know the rock and the fluid properties. From these chapters we will know how the oil and the reservoir rock, how the water, oil and gas, their movement. So in these contents we'll have the reservoir rock characteristic and porosity and permeability, rock and fluid interaction, and the types of the reservoir, and the types of the reservoir drive mechanism. So it's very important. So for the reservoir rock characteristic, to form a conventional reservoir of hydrocarbons, any geologic formation must exhibit two essential characteristics. These are capacity for storage and transmission able to the fluid concerned, and the storage capacity requires a void space within a rock, and the transmission requires that there should be continuous of this void space. So the porosities is like this photo we can see. This is the different. This is the stone, and this is like the pond. The fluid can to the pond of this sonic to movement. So the petroleum is not found in underground rivers or covers, but in pore space between the grains of the porous sedimentary rocks. This is a very important concept. In this photo we can see a piece of the porous sediment rock. The pore space are the white areas between the dark green. It's within such pore space that fluids such as oil, natural gas, or water can be found in the subsurface. The porosity is defined as a percentage or fraction of void to the bulk volume of materials. The porosities of the conventional reservoir may range from about 5% to about 30% of the bulk volume. This is the formula of how to calculate the porosities, where we can see the VP. The VP is the pore and the volume. The VG is the grain volume. VB is the bulk volume of the rock. So the VB, the porosity means VP to VB. Yeah. So the VP equals VB times VG. So we can say the porosity means VP to the VB to VG. It's a percent. So we should very familiar with this formula to calculate the porosities. And factors affecting the porosities, many things can affect this. Here is the factors. The first is grain size. The grain size has no effect on porosities, where round sedimentary that are packed into the same array generates has porosity from 26% to 48% depend on the packing. The third is sorting. The where sorted sedimentars generally have higher porosities than poorly sorted sedimented for the sample reason. If a sedimentar is a range of practic size, then the smaller practic may fill in the voids between the larger particles. And the grain shape. Irregularly shaped particle tends not to pack as dirty as round particle, resulting in higher proportions of the void space. So here is also have the total and effective porosities. The total porosity defined as the ratio of a volume of all pores to the bulk volume of materials, regardless of whether or not all the porosities are interconnect. This is the total. Effective porosities is defined as a ratio of the interconnect pore volume to the bulk volumes, so it's more important. So the primary and secondary porosities. Primary porosity is defined as a porosity in a rock due to sedimentary process. Second porosity is defined as a porosity in a rock which happen after sedimentary process, for example, fraction and recrystallizations The next one, we talk about the porosity measurement, how to measurement porosity. We have three kinds of the method. The first one is boilerless no porosimeters. Second, wet and dry weight method, and also the simulation of the fluids. So the permeability of a rock is measure of the which fluid can flow through a rock. This depends on how well the pore space within that rock are interconnected. This one we can say is a good permeability. It means here is interconnect, is not connect. This one poor permeability is very close and connect the grains is very hard to movement. So the permeability is a measure of the ability of a porous materials to transmit fluid and a potential gradient. The unit of the permeability is mean K is Darcy, named after a French scientist Henry Fenibert Grasbert Darcy, who investigates the flow of the water through the filter beds in 1856. One Darcy it means 0.987 10 double 12 meters. This is the unit. So the generation data equals, it means this is the materials. This is the materials. This is the fluids, and this is the score. So the Q and Q2A is equals the doubles K2U and delta P to delta L. So where the Q is mean flow rate, the K is the permeability, and A is the cross section errors. The mu mean fluid vessel viscosity, and P is pressure, and L is length. So use this formula, we can calculate the K. It's very important about this formula. So this is example from this. We can find the K. This is just a practice. To the Q is like this. A is 1 centimeter quarters and mu 1 cp, and like this we can calculate the K. So the 1 Darcy is defined as a permeate that where permit a fluid of 1 centiposit vessel viscosity to follow at the rate of the 1 cubic centimeters per second through a cross sectionary errors of 1 square centimeter when the pressure gradient is 1 atmosphere per centimeters. Is the 1 Darcy mean. So there are 4 conditions that are required of this equation to be valid. First is laminar flow type. Third, no accumulations. Third, is single phase liquid fluid. And the parameter is not reactive with the flowing fluid. This plot the Q and A against delta P to delta L should yield a single straight line assumed below where the scope is K2 mu and equals fluid mobility. So this is the linear flow to different, we can use the different singer to calculate the permeability. This one can show us as a exercise. We just talk about this one. This is the line, without the angle. It's a Q equals key and A that is equal to the mu and the depth pressures to the L's, we can calculate the key. This is the radial flow. The radial flow is like this. This is where this is H, two difference. So Q and for QA to this, and also the A is the equal. We can say 2 pi H and use this to we can calculate the Q. Finally, it's like this. And also we can average permeability for the parallel sand. We can divide different the types, the K1, K2, Kn, and use the Q, and it means the Q1 to Qn. And also we use this, and finally we can find the average permeability. So the depth is also like this. Finally, we can find this. Can we prove it? Yeah. So now we give the exercise 1 for the different on this slide. Yeah, you can give this to calculate the flow rate. Yeah, the percentage like this. And effective horizontal permeability and pay-zone cycles and reservoir pressures and flowing bottom pressures and bubble point pressures and oil formulation volume factors and oil viscosity and drainage errors and wear-borne radius phase. So please calculate the flow rate. We can give you give you about 5 minutes to about this, and finally to find this to calculate. Okay. Okay, yeah. Please, yeah, remark and note these parameters, and after class to take the exercise to make the calculation of the flow rate. We continue the class. So for permeability measurement, yeah, different types of the methods. The permeability of the core sample can be measured by liquids. The permeameters and gas permeameters. The liquid permeameter, the non-reactive liquid, we can see the paraffin oil. It forced to flow through a core sample in a core holder. A flow rate is measured and the permeability is calculated using general Darcy equation. And the gas permeameters, the non-reactive gas, typically the helium, is used in the measure of the permeability. The gas is flow through the sample and the flow rate of the gas is measured. The figure below illustration the schematic diagram of the Hill's lateral type permeability measured and the steady state flow conditions. So it's lower pressures from here and to here, the core sample. For the core sample, this is the rubbing tubing, and this is the vacuum, and to the flow meter to test the flow meters. The permeability is calculated using flowing modified form of the Darcy equation, which takes into account the gas compression ability during flows. Is Q here? The Q is the gas flow rate, the kg is gas permeability, and A is cross-section errors, and mu is fluid viscosity, and P1 is pressure, inlet pressure, P2 is outlet pressures, and PA is atmospheric pressures, L is net. From this we can calculate the kg. It's like this, so it's also very important, please remember. And the sig pages fraction during gas permeability measures is like this, and it's like this. So including this, the gas permeability depends on the mean pressure of the gas existing at the time of measurements. At no mean gas pressure, gas permeability exceeds liquid permeability. At high mean gas pressure, gas permeability approaching liquid permeability. Slippage effect is a laboratory phenomenon due to no flowing gas pressure, but likely able for gas flow as reservoir condition. So the cabin corrections, this plot. The plot of kg vectors in the inversion of mean flow pressures. Yes, a straight line with slope kb and the intercept of the kb is calculated simple gauge function. Slope is a function of the molecular weight and the molecular size. So finally it's like this, kg and k to this. And also we use the Kenkini effect plot. It's like this. The blue one is the hydrogen, and this dark is the nitrogen, and this is the carbon dioxide. So in this we will talk about rock and fluid interaction. The interfraction tension and capillary pressure and wettability and relative permeability and stock tank oil initially in place. Interfriction tension is very important. Interfriction tension is a force at the interface that acts to decrease errors of the interface. A drop of water can hang down from the edge of the glass tubing using the force at the interface. However, when the interfacing tension is weaker, only a smaller drop can hang on from the edge of the glass. The interphysical tension can be measured using this phenomenon. The reason why surface tension is decreased when something is adsorbed on the surface. The first one is the attraction force between water molecules is greater than that between other molecules because of the hydrogen bondings. At the surface, the attractive force works only from inside, since there is low water on the outside, the air side. So, a water molecule on the surface is strongly attracted towards the inside. This force is called surface tension. However, when something is absorbed on the water surface, interactions between the absorbed molecules themselves and also the absorbed molecule and the water occur at the surface, so that the surface tension decreases. So this photo is talking about the surface interfaction. This is the oil, and this is the intermoleculars. The pulls in all direction can do all direction. This is the moleculars. At the surface, we can say this is the surface film. This is many surface. In the surface, molecules pulled towards liquid cause tension in the surface to here. The another one is wettability. The wettability of liquid is defined as the contact angle between a droplet of the liquid in semi equilibrium on the horizontal surface. This is water. This is water wet. This is oil. This is oil wet. So like this. The wetting angle is given by the angle between the interface of the droplets and the horizontal surface. The liquid is safe wetting when from 90 to 100 and non-wetting where from 0 to 90. You can say this is from 0 to 90 is water wet. This is over 90 to 180 is oil wet. The wetting phase will tend to separate on the solid surface, and a prior solid will tend to imbibe the wetting phase. Rock can be water wet, oil wet, or intermediate wet. The intermediate wet state between the water wet and the oil wet can be caused by a mixed system in which the surfaces are not strongly wet by either water or oil. The next one talk about the capillary pressure. The capillary pressure is the pressure difference exerted across the interface separates two immiscible fluid. is defined as the difference between the pressures in non-wetting and the wet wetting, that is PC equals PNW water to depth P water. For an oil water system, water wet, the PC and P oil to PW. And for a gas oil system, oil is PC, PJ, depth PW. So this is a oil water system. This is water, this is oil, this is PW1, this is PW2. Yeah, we can do PA2 and PW2, PW2 and PW1 to like this. To this places we can say PC and rho W depth rho O to Hg. This is like the pressure. And relative permeability. Relative permeability measurements are made routinely on core samples to define the relative amounts of the fluid that will flow through the rock when more than one fluid phase is floating. Definitions are the KRO is KO to Ka, where oil, water, gas. KR is means relative permeability, and K it means permeability to a specific fluid for oil, water, or gas. So Ka is a theoretical air permeability. So by this we can calculate the difference, the relative permeability. So for the STO2P in place volume of oil is always equal to a surface condition. This is here it means STOIIP means stock tank oil initial in place. It means barrels. The BV is means bulk volume of rock. The phi is means porosities. The SO is oil saturation. The BO is oil formation volume factor reservoir. So from this we can calculate the bottom, the stock tank oil initial in place is 3052 plus BV to the phi to SO to like this. We can calculate the condition, the stock tank oil initial. It's very important. So here also have the exercise. An oil well has been drilled and complete. The production zone has been encountered at depths 5,220 to 5,350 feet. The log analysis shows that the average porosity is 21%, water saturation is 24%, formulation volume factor is 1.7476, and average is 93 acres. So we can calculate the stock tank oil initial pressure. We can use this formula to calculate the barrels. So this one no need. You can just mark in after class to make the exercise. So we talk about the type of the reservoir. The first is oil reservoir. The oil reservoir contains many oil with or without free gas. So can be divided into two. Under saturated oil reservoir is no free gas exists until the reservoir pressure falls between the bubble point pressure. The saturated oil reservoir, the free gas exits the reservoir. So next type is the gas reservoir. So recovery of the hydrocarbon from an oil reservoir is commonly recognized to occur in several recovery stages. First is the primary recovery. The recovery of the hydrocarbons from the reservoir using the natural energy of the reservoir as a drive. The secondary recovery. The recovery aided or driving by the injection of water or gas from the surface to recover the oil. The tertiary recovery, enhanced oil recovery, is EOR, enhanced oil recovery. It means a range of technical labeled enhanced oil recovery that are applied to reservoir in order to improve flagging production. The inferior recovery carried out when recovery from a previous three phases have been completed. It involves drilling cheap production holes between exit boreholes to ensure that the whole reservoir has been fully depleted of its oil. So next one we talking about the drive mechanism. The natural energy of the reservoir used to transport hydrocarbons towards and out of the production well. There are 5 important drive mechanisms or combinations: solution gas driving, gas cap drive, water drive, gravity drainage, and combined or mixed drive. A combined or mixed drive occurs when any of the first 3 drives operate together, or which any of the first 3 drives operate with the aid of the gravity drainage. Solution gas drive. This mechanism, also known as depletion drive, depends on associated gas of the oil. The virgin reservoir may be entirely liquid but will be expected to have gaseous hydrocarbons in solution due to the pressure. As the reservoir depletes due to the production, the pressure falls below the bulb point and the gas comes out of the solution to form a gas cap at the top. This gas cap pushes down on the liquid, helping to maintain pressure. The exsolution and expansion of the dissolved gas in the oil and the water provide most of the reservoir drive energy. So the solution gas drive reservoir is like this. It's like this. This is the initial condition, full of oil. And then during the depletion of oil from here, use the levels of here, the gas to push the oil to the well. So the gas cap drive. In reservoir already having a gas cap, the virgin pressure is already below bulb point. The gas cap extends the deflation of the reservoir, pushing down on the liquid section, applying extra pressure. This is the gas cap drive reservoir. The gas trap at the top here, the gas crossing to push the oil to the well. The presence of the expanding gas cap limits the pressure, decrease the experienced by the reservoir during production. So the water drive. The drive energy is provided by an aquifer that interfaces with oil in the reservoir as the water contacts, we can say OWC. As the hydrocarbons deplete, production continues, and oil is extracted from the reservoir, the aquifer expands slightly. If the aquifer is large enough, this will translate into a large increase in volume, which will push up on the hydrocarbons and thus maintain the reservoir pressure. Two types of the water drive are commonly recognized: bottom water drive and edge water drive. The types of the water drive. This is the bottom water drive is from the aquifer to the push the water to the water, and edge water is like this, the water to push the oil to the well. And gravity drainage. The gravity drainage is the density of difference between the oil and the gas and the water resulting in their natural segregation in the reservoir. This process can be used as a drive mechanism, but is relatively weak and in practice only used in combined with other driving mechanisms. And combination is a practice a reservoir usually incorporated as at least two main drive mechanisms. So for example, this one is use the gas cap and also the gravity and water to push and during the depletion. The secondary recovery. The secondary recovery is a result in the human intervention in the reservoir to improve recovery when the natural drive have diminished to unreasonable low efficiency. Two techniques are commonly used. The first is the water flooding, involve injection of water at the base of the reservoir tube. First is to maintain the reservoir pressure and displace oil towards production well. Second is gas injection. This method is similar to water flooding in principle and is used to maintain the gas cap pressure even if oil displacement is not required. And the tertiary recovery. Primary and secondary recovery methods usually only extract about 35% of the original oil in place. Clearly, it is extremely important to increase this figure. Many enhanced oil recovery methods have been designed to do this, and a few will be reviewed here. They fall into three broad categories: summer EOR, and chemical EOR, and miscible gas. All are extremely expensive, are only used when economical. The first is summer EOR. This process uses heat to improve oil recovery by reducing the viscosity of heavy oil and vaporizing light oil, and hence improve their mobility. The technique includes steam injection, in-situ combustion, injection of hot gas that combustes with the oil in place, increase the related permeation to oil, the micellar and aqueous fluids. Thermal EOR is probably the most efficient EOR approach. The chemical EOR. This process uses chemical added to water in the injected fluids of a water fluid to alter the fluid efficiency in such a way as to improve oil recovery. This can be done in many ways. Examples are listed below. The first, increasing water viscosity, the polymer fluids. The second, decreasing the relative permeability to water, cross-linked polymer fluids, and microwave heating downhole, hot water injection. Also chemical. The chemical EOR process. This is the injector. This is the production wear, injection wear. Inject the water-dry fluid. Inject polymer buffer and polymer fluid to control mobility and surfactation and oil bank, pre-flush, origin instead fluids and together to push the oil. The miscible gas flooding. This method using a fluid that is miscible with the oil. Such a fluid has a zero interfractional tension with an oil and can be principle flushing out all the oil remaining in place. In practice, a gas is used since gas has high mobility and can easily enter all the pores in the rocket, providing the gas is miscible in the oil. Three types of gas are common use: CO2, N2, hydrocarbon gas. So, this is talking about the rock and the fluid property. Also very important to our engineer to know how about the movement of the oil and the gas. So in this we talk about first is the reservoir rock characteristic. We also talking about porosities and how to calculate porosities and permeability, how to measure and calculate the permeability, and also the different types of rocks and fluid interactions, the water, the surface interactions, and also the different types of the reservoir and types of reservoir driving mechanism, like the water and driving and the one primary and secondary and tertiary and give the example of this the driving mechanism. So please let us know. And also here we make some exercise. Please ask the class to make the calculation about this. So now we continue our class. The next chapter is talking about draining operation. It's also very important. In this content, we make the introduction about the draining and types of the oil rigs and rotary draining and working tour, draining procedures, direction draining, and draining problems. So, introduction about the draining team. The draining team comprises of draining contractors, personnel, and noble or trading or fabric, and also the operating company representative is mainly the draining team, draining over departments from this, and also the surface companies like Halliburton, Schlumberger, BJ, Baker Hughes, and also the supplier companies like catering surface, supply boat, and any others. So this is the main comprise of the draining team. And also we talking about the function of the draining engineer. The draining engineer is to prepare drilling programs. Modified drilling program cost is estimated, including AFE. AFE is the authorization for the expenditures, and the BD and bid specification for drilling contractors and drilling contract. There are various drilling contracts: the daily rate, the turnkey, the foot gauge rate, and the incentive, and also to work with geologists on logging program and other specialists such as direction engineer, mud engineer, surface and supplier personnel. So we can say the drilling engineer have at least three functions. First is technical. Second is economic. Third is safety and management. So it's very important. So the types of the drilling rig. All rigs have the same basic components. The land rig is a jackknife and cutter-left rig and proper master. Main design features are portability and maximum operating depth. The rigs are built on location. The third one is marine or offshore rigs. The bottom supporting offshore rigs, submersible floating rig, and drill ship floating rig. Main design features are portability and maximum water depth of the operation. So this is the type of the drilling rig. The land rig, we have heavy land rig, light land rig, helicopter table rig, and the marine rig has the floating rig. It has the semi-submersible and drill ship and drill barge, and the bottom supporting rigs, jack-up, platform, submersibles, a typical classification of the rotary drill rigs. So the types of the oil rig, land rig. The sequence of the operation is as follows. When a land well is drilled, prepare location before rig arrive. Dig the cellar, install conductor pipe, prepare support pad for rig, the campers, and build road, fencing, and dig pits, and sometimes drill water well, and then move rig on the location, rig up, prepare to start drilling. So the offshore drilling rig, two main types: the floating, the bottom supported unit. The floating unit include semi-submersible boater type, column stabilizers, and barge rig and drill ship. The bottom supporting unit include submersible posted barge, bottle type submersible, article submersible, and jackups and platform. So the semi-submersible. This floating drilling unit has cannot, when fluid with sea water, cause the structure submerged to a predetermined depth. Although it's moved by wave action, it sits no with large part of its structure, and water combined with 8 huge mooring anchors made it very stable installation. This type of rig drills a hole in the seabed, then it moves to the next location. With evidence, technical semi-subsets can drill in water depth over 5,000 feet. The able. This is the stable semi-recess below the water while draining. This is the fuel. This is column. This is the surviving capture, and this is the ray. This is the drill flow, and it's the main deck. It's like this. The second platform. This immobility structure can be built from concrete or steel or resource on the seabed. When oil and gas is located, a platform may be constructed to drill further wells at this site and also to produce the hydrocarbon. And steel jacket platform. Most common type of the platform consists of the jacket, a tall vertical section made of the tubular steel members, supported by pilots driving into seabed. Additional sections on top of the jack provide space for drilling rig, crew quarters, and other equipment. This is the steel jack platform. Concrete gravity platform, and built from steel reinforced concrete. Intersection and concrete are the dominant feature of this platform. Sometimes special concrete cylinders are fixed at the base of the adjacent the sea floor to store crude oil. And steel section platform, specifically for using in cold areas where faster moving tidal currently carry pack of ice that can destroy the steel jacket. The caissons are made of 2 layers of thick steel to prevent ice damage. And compliant platform is using rigid platform in water much over 1,000 feet depth. It's not practical, very much expensive to build. In deep water, most companies use compliant platform, which contain fewer steel parts and are lighter than rigid steel jacket. It's gauge tower platform and tension neck platform. This is the compliant platform. It's gauge tower platform. This tension neck platform. The third one is jack up. This is a mobilable. It's a modular drilling rig, different from the semi-submersible. Instead of floating over its drilling location, the jack-up has long leg structures, which is lowered to end into the seabed, rising the rig out of the water. The obvious limitation with this type of installation is the depth of the water it can operation in, the maximum being 500 feet. The drill shape. As the name suggests, this is a shapes drill vessels. Unlike the semi-submersible and the jacket, it doesn't require tugboats and towage location. Although they are not as stable as semi-submersible, they also drill in very deep waters. And F5 is FPSO, floating production storage offshore loading. They are attached to a seabed wellhead and they produce and store the oil until another tanker takes it from it. They are used to produce from small wells where it would be too expensive to build a platform. Rotary drilling. Rotary drilling uses a sharp rotating drill bit to dig down through the earth's crust. The spin of the drill bit announces the penetration of even the hardest rock. The actual mechanism of modern rigs are quite complicated. In addition, technical advances so rapidly that new innovations are being introduced consistently. A rotary drilling rig with some of its major components identified is illustrated in the next figure. This is the rotary drilling rig. We can see it includes the derrick and also the hose, and use the tributary blowout preventer and the spare pile and engine turnout and motor casing, electric generator. This is the bit and drill. This is the first casing, the drill sharing, the drill collar with the drill bits and to drill the formation. The rotary drilling, the basic drilling system have the four groups of the components: the primer movers, the hoisting equipment, the rotating equipment, and also the circulating equipment. For the primer movers, the primary mover in a rotary drilling rig are those pieces of equipment that provide the power of the entire rig. Recently, while diesel generates steel composed the majority of the power source on rotary rig, other types of engine are also in use. Some rotary rig may use electricity directionally from power line. Most rotary rigs this record 100 to 300 horsepower, 1000 to 3000 horsepower, while shallow drilling rigs may record as little as 5000 horsepower. The energy from these premium movers is used to power the rotary equipment, the hoisting equipment, and the circulating equipment. The second is hoisting equipment. The hoisting equipment on a rotary rig consists of the tools used to rise and lower whatever other equipment may go in or come out of the well. The most visible parts of the hoisting equipment is the derrick, the tall tower-like structure that extends vertical from the well hole. The hoisting system is made up of the jaw workers, derrick, chrome block, traveling block, hog, and wire rope. If a drill bit needs to be changed, either due to tears or a change of the subsurface rock, the whole string of the pipe must be raised to the surface. The hoisting equipment. The hoisting equipment is used to raising all of this equipment to the surface so that the drill bit may be replacement. So it includes chrome block, the drill line, the derrick, the fast line, and the dead line, the traveling block, the hog, the draw walk, the dead line anchor, and storage rear. The hoisting equipment, this is also very important. While it's from the well like this. The derrick of the master, whenever the drill stem is suspended by the traveling block and drill line, the entering node rests on the derrick. The standard pyramid derrick is a structure with four supporting necks resting on a scholar base. In comparison, a mast is much more slender and may be thought of as setting on one side of the rig floor or workspace. The derrick is erected on a substructure which supports the rig floor and rotary table and provides workspace for the equipment on the rig floor. The derrick and its substructure supports the weight of the drill stem and wall ties. Whenever it's suspended from the crow block or resting the rotary table, the height of the derrick doesn't affect its load-bearing capacity, but is a factor in the length of the section of the drill pipe that can be removed. So the traveling block, the crow block, and the drill line and hook, all of these used to connect the supporting derrick with the load of drill pipe to be lowered into or withdrawn from the bone holder. During drilling operation, this load usually consists of the weight of the drill pipe, drill collars, and drill bits. The drill line passes from the jaw works to the top of the derrick. From here, it shifts between the crawling block and traveling block to give an 8-10-12 line suspension. It's then clamped to the rig floor by the deadline anchor and blocks the drill line and hook. This is suspended from the traveling block on standard under standard drilling system. It's the hook which when drill carries the swivel and the canny, and when tripping it lifting the drill string. For the drill works, the draw works is mechanism commonly known as a hoist. The main purpose of the draw workers is to lift the drill string out of and to lower it back into bone hole. The drill line is drilled, spurred on a drum in the drill works. When engaged, the drum turns and either reels in the drill line to rise the traveling block or lets out of the drill line to lower it because of the drill stem is attached to the block, is raised and lowered. One outstanding feature of the drill works is the brake system, which enables the driller to easily control a load of the thousands of pounds of the drill pipe or casing. An integral part of the drill works is the gears, the transmission system. This gives the driller a wide choice to speeds for the hoisting the drill string. The drill works also have a drive sprocket that drives the rotary table by means of a heavy dart chain. In some cases, however, the rotary table is driven by an independent engine or electric motor. Another feature of the draw works are the two cat heads. The make-up cat head on the driller's side is used to spin up and tighten the drill pipe joints. The other, located opposite of the driller's positive position on the drill works, is to break out cat head. It's used to loosen the drill pipe when a drill pipe is withdrawing from the borehole. For the rotating equipment consists of the components that actually serve to rotate the drill bit. Rotating equipment from top to bottom consists of swivel, a short piece of pipe called the canny, rotary table, top drive, the drill string, and bit. A component called the swivel, which is attached to the hoisting equipment, carries the entering weight of the drill string, but allows it to rotate freely. The drill bit is located at the bottom end of the drill string and is responsible for actually making contact with the subsurface layers and draining through them. So the rotating equipment is also to drill the formations, to transfer the torque and the force. There are four main types of the drill bits, each suited for practical conditions. The steel tooth rotary bits, most the basic type. Insert bits is tungsten carbide inserts and polycrystalline diamond compact bits and diamond bits. Diamonds implants in them. Diamond bits are 40 to 50 times harder than the traditional steel bits. So this is the rotating equipment. Rotating system. The figure at the bottom left indicates the comparative size of the drill pipe and the drill collar. So for the rotating system, at the bottom is the bit and the drill collar and the drill pipe, and for we can see this is the swivel and the canny. Canny to here is the canny pushing, the canny elevator and rotary table, and use the force to rotation to transfer to the bit to drill the formation. And the swivel hangs from the draining hawk by means of large bells or handles. The swivel is not rotate, but allow everything below it rotate. The draining fluid is introduced into the drill stem through a geoselic connection on the sliver, which is connected to the rotary hose. The power swivel. When a top drive system is used, the swivel is replaced by power swivel. The power swivel performs the same function as the normal swivel, but is also associated with the transmission system used to rotate the drill string instead of rotary table transmission to this motion. And the canny is approximately 50 feet long, square and hexagonal on the outside, and hollow throughout to provide the passageway for the drill fluid. Its outer surface engaged corresponds score and hexagonal surface in the kidney pushing. The kidney pushing fits into a part of the rotary table called master pushing. Powered gels in the rotary table rotates the master pushing and thus a kidney pushing. The kidney pushing will rotate the kidney and everything below it to rotate. The drill string. The drill string is made up of the drill pipe, drill collar, and specular servers through which the drill fluid and the rotation power are transmitted from the surface to bit. And the drill pipe and the drill collar comes in section or joints about 30 feet long. The most common used diameters of drill pipe are 4-inch, 4.5-inch, and 5-inch OD. The purpose of drill collar is to put extra weight on the bit, so they are usually larger in diameters than drill pipe and heavy, thicker walls. Drill pipe and drill collar have thread connection on each end. On drill pipe, the thread connection are called tool joints. Tool joints are steel rings that are welded to each end of the joint of the drill pipe. One tool joint is a pin male connection, and the other is a box female connection. Specialty servers, the word serve refers to any short length of pipe, collar, casing, and others with a definite function. The drill bit. At the bottom of a drill string is a bit which drills the formation rock. Most common types are roller cone bits and diamond bits. The bit size range from 3-4-inch in line to 5 centimeters to 26-inch in diameters. The most commonly used size are 17.5, 12-1-4, and 7-7-8, and 6-1-4 inches. The roller cone bits usually have 3 cone-shaped steel devices that are free to turn as the bit rotated. Several rows of the teeth or cutters on each cone scrape, gouge, or crush the formation as the teeth roll over it. 2 types, milled teeth and tungsten carbide inserts. Most of the roller cone bits are jet bits. Draining fluid exits from the bit through louvers between the cone, thus create high velocity jets of mass. This will help lift cutting away from the bit. The last one is the circulating system. There are a number of main objectives of this system: the cooling and liberating the drill bit, cooling well pressure, removing debris and cuttings, coating the walls of the well with a mud cake. The circulation system consists of the draining fluid, which is circulated down through the well hole. The most common liquid draining fluid, known as mud, may contain clay, chemical, wetting materials, water, and oil. The circulating system consists of a starting point, the mud pit, where the draining fluid ingredients are stored. The mixing and also have the function of mixing takes place at the mud mix hopper, from which the fluid is forced through pumps up to swivel and down all the way through the drill pipe, emerging through the drill bit itself. From there, the draining fluid circulates through the bit, picking up dissolves and draining cuttings to be circulated back up the well, traveling between the drill string and the walls of the well, also called the annular space. Once reaching the surface, the draining fluid is filtered to recover the reusable fluid. This is the circulating system. We can say, the fluid from the mud pump and transferred to the pipeline to the hose and to the swivel, and then to the canny and to the rotation from the drill pipe to the drill pipe and to the bottom of the drill bit, and then from annual hole and to the come out from the well and for the mud return line and to the factory to circulation, and then to the mud pit and the mud tank, and then transfer the mud tank into the circulation again. The draining fluid, major direct function of draining fluid is to keep hole free of cutting, to exert sufficient hydrostatic pressure on the formation, and to prevent walls from caving, and to cooling and liberation of the drill string, and to reduce friction between the hole and the drill string, to help suspend the weight of the drill string and the casing, and to deliver hydraulic energy to the formation and the bit. One critical function of the draining fluid, when formation pressure is more than hydrostatic pressures, a kick occurs. An uncontrollable kick may cause a catastrophic blowout, perhaps the worst disaster during draining operation. The effects of the blowout are loss of life, loss of draining equipment including the rig, loss of the well, and loss of oil and gas reservoir, damage to the environment. So the blowout is the heaviest incident for the draining operation. For the well control, Draining fluid provides the first line of the defense against blowout. The hole full of mud that weighs the right amount and the proper density will not blow out, but sometimes an impact occurs. The second line of the defense against blowout is the blowout preventer (BOP). When closed, they form a pressure-tight seal at the top wear and prevent the escape of fluid. This is the BOP, yeah. This is the BOP, yeah. For the wear heading casing Christmas tray and Kenny, the BOP static and the inject header. First, the drilling procedures. First, surface pipeline is set. A shallow hole is drilled after several hundred feet deep. A string of surface casing is inserted into the hole and cemented in place. The surface casing is 10 to 20 inches in diameter, which allows the drill string of the bit pass through it for deeper drilling. After surface casing has been set, the deeper drilling begins. A smaller bit is running inside the surface casing and continue drill to the desired depth. The same process is repeated for the intermediate and production casing. The casing accessories include centralizer. The centralizer is to keep the casing in the center of the hole so that the cement distributes even around outside of the casing. And the structures help remove wall cake so that the cement can form a better bond. And the casing shoe or guide shoe fits onto the end of the last joint. It prevents the casing from sagging in irregularity in the bone hole as is lowered. And the floating collar, a special coping used one or two joints above the guide hole shoe, contains one-way valve which prevents drilling mud from entering the casing and also prevents cementing from flowing up the casing. Cementing the casing. Cementing used in over oil well cementing is Portland cement. It usually consists special additive to make it suitable for cementing a particular well. For example, a retarder requires to slow down the setting time of cementing. The cementing crew mixes the dry cement with water to form cement slurry. The powerful cementing pumps move the slurry through a pipe to a special valve made up on the topmost joint of casing, the cementing head or plug container. As the slurry arrives, the bottom of the plug is released, which presses the slurry down the casing. This plug will keep mud from contaminating the cementing slurry. Cementing casing. The plug will stop the floating collar, which continual pump pressure will break a seal in plug and allows the slurry to pass through it. The slurry flows out through the floating collar and the guide shoe and starts up the antlers until annulus is filled. The crew releases a top plug and pumps a liquid called displacement fluid, normally salt water, behind the top plug. When the top plug comes to reset on the top plug, the crew shuts down the pump and allows the slurry to harden. Next one, we talk about the directional draining. If it's often difficult to place a draining rig directly over the spot where a well should be drilled. This is particularly true offshore-onshore, where a number of the wells must be drilled from the same location. Directional draining is the process of draining a covered well in order to reach a target that is not directly beneath the drill site, like this. Directional draining. The calculation for directional draining have become more sophisticated. The earlier method used was web stock, which involves placing a wedge. We use the web stock, use a wedge-shaped piece of the steel at the bottom of the hole to force the bit of the desired angle. A more recent development in directional draining has been use of downhole motor. The draining problems: stuck pipe, loss circulation, bone hole instability, mobile formation, undergouge hole, cakes and blowout. The first is stuck pipe or pipe sticking. The definition is when part of the drill pipe or collar are stuck in the hole. If pipe cannot be rotated or pulled and circulation is good, then pipe is probably wall stuck. The cause of the pipe sticking: the first is differential wall sticking. The second is mechanical sticking. The third is key setting. For the differential or wall sticking, differential is the pressure different around the circumference of the drill collar or pipe. The wall sticking is caused by pipe is held by suction force resulting from overbalanced hydrostatic pressure forcing filtrates into a permeability zone, which leaves a thick mud cake on the wall of the hole. And third, also the porous and permeated formation, and also the motionless drill strings. Second is the mechanical sticking. A drill pipe can be stuck mechanically when cuttings and sloughing formation pack off the annular space around the drill string, especially during a pump shutdown period, and draining through several layers of the formation different heights, and junk drop from the surface. The drill string is run too fast until it hits the bridge, a tight spot, or the hole bottom. All this can cause mechanical sticking. The third one is key setting. It means a phenomenon happens at the dogleg, where a new hole is created by drill string until the drill pipe is stuck into the wall. When it passes through a dogleg, it tries to strengthening, and thus creating a natural force which causes the drill pipe joint to dig into the formation as a deadlock ball. A key set can only be formed if the formation is really soft and hand weight below the dead leg is big enough to create a substantial lateral force. This problem can be identified when the drill string can be moved downwards but not upwards. The second kind of the problem is loss circulation. One of the major problems in drilling operation. It often occurs in almost every formation and at virtually all depths. It can occur when hydrostatic pressure of mud exceeds the breaking strength of the formation. So the deflation should be partially or completely loss of the draining fluid during draining, circulation, or running casing. The types of the loss circulation. Those types inherent in the formation. The first is porous, permeability, and unconsolidation formation. Because this one is the fluid can enter in. Second is cavernous or irregular formation. And thirdly is lateral fractures in formation, like the faults, joints, and fissures. And this opening caused by poor drilling practice. Also, the poor drilling practice include fractures caused by high mud weight or pressure surge can cause the loss of the circulation. The third one is shear problem. We can also call the bone hole instability. The shale, the sedimentary rock formed by depositing and compaction of the sedimentary and contains of the clay, silt water, cauteries, and feldspar. And third one is compact or unconsolidated rock depend on water content. So the definition of shear problem and bone hole instability is a condition where the shear section contains bentonite or other hydrotapeability clay which continually absorbed water from the mud and then expanded and swell and sloughing into the hole, and also cause the hole instability resulting from the drill shear section. And other terms is sloughing shears, heaving shears, or running shears can cause this problem. How to prevention of the sloughing shears? Use suitable mud system to inhibit hydrogen and high K or K content, OBM, and oil emulsion, and this to decrease the tendency of mud to hydrated water sensitive clays. And second, increase the circulation rate for more rapidly remove the particles. The third one is increase mud density for for greater wall supporting, and also decrease water loss of mud and avoid fast trip or swabbing of the hole, and also keep flow properties and annual velocities at such a level as to ensure good hole cleaning. The fourth type is the mobile formation. A salt or shell can squeeze into the wear bone because it's being compressed by the overboard force. The deformation results in decrease in wear bone size, causing problems running BHAs, locking tools, and casing and stuck pipe. A deformation occurs because the mold weight is not sufficient to prevent the formation squeezing into the wear bone. And once broken, the hole will become enlarged. So the prevention actions, the first one is identify salt dome. The second one is monitor mold colorities and mold resensitivity. The third one is maintain sufficient mold weight and select an appropriate mold system that will not aggravate the mobile formation, and also plan frequent reaming vapor trips, practically for this section of the hill, and also slow trip speed before BHA entering the suspect areas, and also minimize the open hole exposure time of these formations. Use these actions to avoid the mobile problems like this. The 5 is under gouge hole. When draining the hard abrasive rock where the beach and the stabilized gouge and result in smaller than gouge hole. When a subsequent in-gouge bit is running, it encounters resistance due to the under-gouge section of the hole. And also, if the stream is running into the hole quickly without reaming, the bit can jump in the under-gouge hole section. This mechanic normally occurs after running a new bit, after coring, when a PTC bit is running after a roller coring bit, and also when drill abrasive formation can cause the under-gouge hole. And 6 is kick and blowout. Kick, it means an entry of formation fluid, the gas, oil, water, into the wear bone during draining. The blowout is uncontrolled flow of the formation fluid, the gas, oil, water, from the wear bone. Kick and blowout can occur when hydrostatic pressure of mold is lower than the formation pressure, then cause the formation fluid out of the board can cause the kick and blowout. So the cause of the kick and blowout and draining into high pressure zones, abnormal pressures, and also swabbing when coming out of the hole is too fast, and the improper wheel fill up on trips, And also the noise circulation during drilling or cementing can also cause the cake and blowout. So, in this we talk about the drilling operation. So later we will show one video about the drilling whole process to let you more clear about the operation. Now, we from the video to more familiar about the drilling hole operations.
Geologists and geophysicists have agreed on the existence of a prospect, a potential field. In order to find out if hydrocarbons are indeed trapped in the reservoir rock, we must drill to hit them. Bearing in mind the knowledge acquired about the substratum and the topography of the land, the best position for the installation of the drilling equipment is determined. Generally, it is vertically above the point of maximum thickness of the geological layer suspected of containing hydrocarbons. The drillers then make a hole in conditions that are sometimes difficult. Of small diameter, from 20 to 50 centimeters, this hole will generally go down to a depth of between 2,000 and 4,000 meters. Exceptionally, certain wells exceed 6,000 meters. One of them has even exceeded 11,000 meters. Certain fields can be buried at a depth equivalent to the height of 12 Eiffel Towers. The derrick is the visible part of the drilling rig. It's a metal tower several tens of meters high. It's used to vertically introduce the drill strings down the hole. These drill strings are made up of metallic tubes screwed end to end. They transmit a rotating movement, rotary drilling, to the drilling tool, the drill bit, and help circulate a liquid called mud, because of its appearance, down to the bottom of the well. The drilling rig works like an enormous electric hand drill, of which the derrick would be the body, the drill strings, the drive, and the drilling tool, the drill bit. The most usual tool is an assembly of 3 cones, from which comes the name tricone, in very hard steel, which crushes the rock. Sometimes, when the rock being drilled is very resistant, a single block tool encrusted with diamonds is used. This wears down the rock by abrasion. Through the drill pipes, at the extremity of which the drill bit rotates, a special mud is injected, which the mud engineer prepares and controls. This mud cools the drill bit and consolidates the sides of the borehole. Moreover, it avoids a gushing of oil, gas or water from the layer being drilled by equilibrating the pressure. Finally, the mud cleans the bottom of the well. As it makes its way along the pipes, it carries the rock fragments, cuttings, to the surface. The geologist examines these cuttings to discover the characteristics of the rocks being drilled and to detect eventual shows of hydrocarbons. The cuttings, fragments of rock crushed by the drill bit, are brought back up to the surface by the mud. To obtain information on the characteristics of the rock being drilled, a core sample is taken. The drill bit is replaced by a hollow tool called a core sampler, which extracts a cylindrical sample of several meters of rock. This core supplies data on the nature of the rock, the inclination of the layers, the structure, permeability, porosity, fluid content, and the fossils present. After having drilled a few hundred meters, the explorers and drillers undertake measurements called loggings down the hole by lowering electronic tools into the well to measure the physical parameters of the rock being drilled. These measures validate or invalidate or make more precise the hypotheses put forward earlier about the rocks and the fluids that they contain. The log engineer is responsible for the analysis of the results of the various loggings. The sides of the well are then reinforced by steel tubes screwed end to end. These tubes, called casings, are cemented into the ground. They isolate the various layers encountered. When hydrocarbons are found, and if the pressure is sufficient to allow them to come to the surface naturally, the drillers do a flow check. The oil is allowed to come to the surface during several hours or several days through a calibrated hole. The quantity recovered is measured, as are the changes in pressure at the bottom of the well. In this way, a little more knowledge is gained about the probable productivity of the field. If the field seems promising, the exploration team ends the first discovery well and goes on to drill a second, even several others, several hundred or 1,000 meters further away. In this way, the exploration team is able to refine its knowledge about the characteristics of the field. The decision to stop drilling is made only when all these appraisal wells have provided sufficient information either to give up the exploration or to envisage future production.
And then we are sure about the directional draining.
Traditionally, drilling was done vertically, straight down into the ground. While effective, this method limits access to the oil and gas reservoirs that aren't directly below the rig. That's where directional drilling comes in. Directional drilling allows engineers to guide the wellbore to deviate from the vertical path, enabling us to reach oil and gas reserves that are even located kilometers away. With directional drilling, the wellbore can be steered at different angles. We use advanced technologies like downhole motors and steerable drill bits, which are designed to change the direction of the wellbore in real time while drilling. These tools are equipped with sensors that send data back to the surface, allowing drillers to make precise adjustments, guiding the well towards its target. Think of it like driving a remote-controlled car underground, but way more complex. But what is the path that will be followed to reach the target? Let's talk about well profiles. First, what exactly is a well profile? In simple terms, it is the path a well takes from the surface to the reservoir. Let's start with the vertical well, the simplest and most traditional profile. It is drilled straight down with no deviation. Vertical wells are still widely used when the target reservoir is directly below the drilling site. Next, we have the build and hold profile, also known as the J profile. In this design, the well starts vertically, then gradually builds an angle until it reaches the desired inclination, and it holds that angle until it penetrates the reservoir. This profile is used when the target reservoir is not directly below the drill site. It is common in offshore drilling, where we need to reach reservoirs located miles away from the platform. Up next is the S profile. Like the J profile, the well starts vertically and builds an angle, but here is the twist. It drops back down to a more vertical angle near the bottom. This profile is ideal for reaching deeper reservoirs that are horizontally offset but at a different depth, making it a bit more versatile than the J profile. Now for the horizontal wells, which is one of the most powerful applications of directional drilling. Once the drill bit reaches a certain depth, it curves and drills horizontally through the reservoir. This method is especially useful for shale formations and tight oil reservoirs, where the oil and gas are trapped in narrow layers of rock. By drilling horizontally, we expose much more of the wellbore to the oil-rich rock, significantly increasing production rates. If you thought horizontal wells were long, wait till you see the extended reach wells. These wells follow a similar horizontal trajectory but are drilled over much longer distances. They are perfect for accessing distant reservoirs from a single surface location, which is especially useful in offshore drilling. Next is the multilateral well. This advanced profile has a main wellbore with multiple branches extending into different sections of the reservoir. Multilateral wells are ideal for maximizing production from a single well by tapping into various parts of the reservoir at once. Lastly, let's talk about sidetracked wells. Sometimes things don't go as planned. Maybe there is an issue like a stuck pipe, or we need to access a different part of the reservoir. That's when we drill a secondary wellbore of the original, known as a sidetrack, to bypass the problem or hit a new target. So, why use directional drilling? One key benefit is increased access to oil and gas reservoirs that were previously unreachable with traditional methods. It also reduces the number of drilling sites needed, which means less surface disturbance and a smaller environmental footprint. In fact, with just one rig, we can drill multiple wells radiating outwards, making it more efficient and cost-effective. This makes directional drilling particularly useful in urban areas or environmentally sensitive regions where surface drilling is limited. Of course, directional drilling is not without its challenges. Maintaining wellbore stability while drilling at different angles can be tricky, and downhole equipments need to be extremely durable to withstand high pressures and temperatures. But with advancements in automation and AI-driven drilling technologies, the future of directional drilling looks bright. So that's a quick look at how directional drilling is revolutionizing the oil and gas industry. It is efficient, cost-effective, and helps us unlock oil and gas reserves that were once out of reach. If you enjoyed this video, don't forget to like, subscribe, and hit that notification bell so you don't miss out.
Okay, thanks everyone. Yeah, this in this course we talk about drilling operations. Yeah, we make the introduction of the drilling operations and also the different types of the oil rigs and the rotor drilling, the full system about the lift hosting equipment system and circulation, and also the energy, and also the others, the full main trainings, and also talking about working tools, about kick and blowout and how to control this, and also the training procedures. And finally, we use the video to the whole process about the training operation, and also the direction of training and the training problems, the training problem and the prevention actions. I think from this course, yeah, we have from our workers and the training engineer can totally understand the how about the training process. So next to after the class to more clear from some video, find some document to more clear about the training process. Okay, thanks.